Hi, I'm Mark Barsamian. In this video, I'll be discussing properties of relations on sets. So this material is from section 8.2 of the book, titled Reflexivity, Symmetry, and Transitivity. So we'll be discussing the definition of reflexive relations, symmetric relations, and transitive relations. We'll be doing lots of examples verifying those properties for given relations. And then we'll do a couple of examples involving proving or disproving abstract statements about those properties. Corresponding homework is this short assignment of 4 problems from section 8.2. So let's start by recalling our definitions. Remember that an ordered pair is one of these things, 2 symbols separated by commas in parentheses. A Cartesian product of sets is well, we're going to be most interested in Cartesian product of 2 sets of this form. So that's the set of ordered pairs, where the left element of the ordered pair is an element of the left set, and the right element of the ordered pair is an element of the right set. So that's the Cartesian product. It's the set of all ordered pairs of that form. And then remember the definition of relation. If A and B are sets, then a relation from A to B is just simply a subset of A cross B. So it's a set of ordered pairs. And we have some additional notation. We say X, R, Y to mean that the pair X comma Y is in the set that is that relation. And we speak this saying X is related to Y. Now we write X R slash Y, we speak that X is not related to Y, and that means this, that ordered pair X comma Y is not an element of the set that's that relation. Now today we're going to be talking about relations on a set. That means a relation from set A to itself. So in other words, it's a subset of A cross A. So a relation R from a set A to A is a subset of A cross A. If R is a relation from A to B, then we have a relation called the inverse relation, denoted R superscript -1. It's a relation from B to A, and it's defined this way. The ordered pairs in R inverse are these ordered pairs, Y comma X, such that the corresponding pair X comma Y is in the relation R. So again, to say that an ordered pair Y comma X is in R inverse means that the ordered pair XY is in R. In this section, we're going to discuss 3 properties that relations may or may not have. So these properties are properties that we talk about for relations on a set. So we say that a relation R on a set A is reflexive to mean this. Every element of A is related to itself. And so that would be written formally this way. For every element of A is related to A. Now this sentence is also symbolically noted this way. For every A in the set capital A, this ordered pair A comma A is an element of the relation R. Now we're also going to be interested in talking about relations that are not reflexive. So to say that R is not reflexive means that, well, just simply the negation of that is true. Well, if you take the negation of that, you get this. There exists an element of set A such that this ordered pair A comma A is not an element of the set R. That is, there exists an element A in the set capital A such that, here I have a typo, A is not related to A. That is, there exists an element of A that is not related to itself. That's what it means to say that a relation is not reflexive. We're also going to be talking about symmetric relations. This is something that applies to relations on a set. So we say that a relation on a set A is symmetric to mean this. If one element of A is related to any second element of A, then the second element is also related to the first. So for all pairs A comma B in set A, if A is related to B, then B is related to A. And another way of writing that is, this should say for all A and B, if the ordered pair A comma B is in the relation, then the ordered pair B comma A is also in the relation. So that's what it means to be symmetric. Now we're going to be interested in knowing when relations are not symmetric. That just simply means that the negation of this is true. So the negation of that would be this. There exists elements A and B in set A such that A is related to B and B is not related to A. So the ordered pair A comma B is in the relation, and the ordered pair, this should say B comma A, is not in the relation. So in other words, there exist two elements of A such that the first is related to the second, but the second is not related to the first. That's what it would mean to be not symmetric. There's one more property of relations we're going to be interested in. We say that a relation is transitive. This word applies to relations on a set. We say that a relation R on a set A is transitive to mean this. If one element of A is related to any second element, and that second element is related to any third element, then the first element is also related to the third. So in symbols, for all A, B, and C, if A is related to B and B is related to C, then A is related to C. And so in ordered pair notation, for all A, B, C in set A, if the ordered pair AB is in the relation and the ordered pair B comma C is in the relation, then the ordered pair A comma C is also in the relation. And we'll be interested in knowing about relations that are not transitive. So that will mean that the negation of this is true. That means here we should have there exist A, B, C. There exists A, B, C in set A such that A is related to B and B is related to C, but A is not related to C. So that means the ordered pair A comma B is in the relation, and the ordered pair B comma C is in the relation, that is in the set R. But this ordered pair is not in the set R. So that's what it means for a relation to not be transitive. So what we're going to do today is a bunch of examples where we consider relations and figure out what properties they have. So the first examples will just be involve examples of relations on a set. So here we have a set capital A. It's those four numbers, 0, 1, 2, 3. And here's our relation. R is that set of ordered pairs. So let's illustrate R using a table and a directed graph. So there's a table for R and there's a directed graph for R. Is R reflexive? Well, the answer is no. We have to give a counterexample though, because remember, to say that a relation is not reflexive means this existential statement. There exists an element in set A that's not related to itself. So notice that that cell is empty, so 1 is not related to itself. Now notice we can observe that this relation is not reflexive in other ways. Remember that for a relation to be reflexive, every element would have to be related to itself. That means every cell in the main diagonal of the table would have to be filled in. So if any of those cells on the main diagonal are empty, then the relation is not reflexive. Also, in terms of the graph, for a relation to be reflexive, every element has to be related to itself. That would mean that you'd have to have loops on every element. One would have to be related to itself, which would show up by a loop. So we look for loops on a graph to figure out if the relation is reflexive, and we look for cells in the main diagonal of the table. Now, is R symmetric? Well, remember what that means. To say a relation is symmetric means if you have an ordered pair A comma B that's in your set, that's your relation, then the ordered pair B comma A is also in the set. Well, look, our relation only has these two ordered pairs. And so 2, 3 is in the relation, and 3, 2 is in the relation. So this is symmetric. Now, how does that show up in the table? Well, notice that pairs of the form A, comma B, and B, comma A, pairs of that form show up as being flipped across the main diagonal. So every element in this table has a mirror image across that main diagonal that's also filled in. So that is a giveaway that this relation is symmetric. In terms of the graph, every arrow has an arrow going the other direction. So it's easy to see from graphs whether a relation is symmetric or not. Is relation R transitive? Now that might seem kind of hard. To say that R is transitive means for all ABC, if A is related to B and B is related to C, then A is related to C. Now this says for all ABC in the relation in set A. That has to be true. If you go down and look at our relation, it doesn't seem like we have to worry about that because there's not even a third number involved in any of our ordered pairs, just 2s and 3s. But look at this. Notice that 2 is related to 3 and 3 is related to 2, but 2 is not related to 2. That's one of these things. 2 is related to 3, 3 is related to 2, and 2 is not related to 2. There's nothing here that says the letters A, B, and C have to be different elements. They could actually be the same element. So this tells us that the relation is not transitive. Now, how does that look in our illustrations? I don't actually have a good way of pointing that out in this table. But I will point this out. Notice that there's a path from 2 to 3 and then back to 2. So that's like a broken path. You could think about that as like if you're booking a flight on an airplane. That's a flight with a connection. There's no direct flight from 2 to 2. There's no non-stop path from 2 to 2. Well, that's the idea of not being transitive. To be transitive, every segmented path would have to have a direct path that will get you there without any stopovers. Let's go on. Example 2. The same set A, 0, 1, 2, 3, define relation R to be this set of ordered pairs. So again, we're going to illustrate R using a table and a graph. All right, there's our table, there's our graph. Is R reflexive? You can see clearly that it's not because there's no loop there, there's no loop there, there's no loop there. These cells on the diagonal are not filled in, same thing. So we just need to give one of those as an example that illustrates why R is not reflexive. Is R symmetric? Well, remember what that means. To say a relation is symmetric means that if A is related to B, then B is related to A. In terms of the table, it means that the table has to be symmetric across the main diagonal. And you can see that it's not. This cell is filled in, but this cell is not filled in. And you can see that it's not because here we have an arrow from 0 to 1, but there's no arrow back from 1 to 0. So the answer is no. 0 is related to 1, but 1 is not related to 0. What about transitivity? Remember what that means. If A is related to B and B is related to C, then A is related to C. Well, remember what I talked about before in terms of airline flights. Look at this map of flights that are available. For every segmented flight, is there a non-stop option? Yeah, the only segmented flight we have is this one, from 0 to 1 and then 1 to 2, and there is a non-stop flight available. So yes, transitive. Let's go on. Another example on the same set A, define this relation. Illustrate that relation using a table and a graph. Is this relation reflexive? Well, you can see no, because there's no loop there, there's no loop there. These two cells in the diagonal are not filled in. So this relation is not reflexive. Is it symmetric? Yes, because you can see that this table is symmetric across the main diagonal. Is this relation transitive? If not, give a counterexample. So again, this is confusing because the definition of transitivity involves 3 letters, A, B, and C. But we've seen that those don't have to be distinct letters. But the idea is, think about how a relation would fail to be transitive. You'd have to find 3 elements, A, B, C, such that A is related to B, and B is related to C, and A is not related to C. In terms of the graph, you'd have to come up with some example of a segmented flight, basically, a segmented path that had no direct path as an alternative. Well, there are no segmented paths, so this relation is transitive. So there are no examples that show this relation failing to be transitive. So it's transitive. Let's go on. Now we're going to do some relations on the set of real numbers. We're going to define a relation R, so that's not bold, and this is bold. So we have a relation on the set of real numbers. We're going to define it this way. We're going to say that xry means that x minus y equals 2. And now we can solve this equation for y. This would be y equals x minus 2. So we start by illustrating the relation using a graph. So there's a graph of the relation. It's just a graph of this equation. All the ordered pairs in the xy plane that satisfy this equation are the ones on that blue line. Is R reflexive? Now what does that mean? Remember that reflexive means that every element of A is related to itself. Well, for a number to be related to itself, for instance, the number 1, for it to be related to itself, that point would have to be on our graph, but it's not. 1 is not related to 1. In other words, if I try to build this equation, that equation is false. Now, you can see that for a relation to be reflexive, a relation on the set of real numbers, that whole main diagonal would have to be part of the relation, part of the graph. And so if any part of that main diagonal is missing, the relation is not reflexive. Is the relation symmetric? Now what does that mean? That means if A is related to B, then B is related to A. Now if something is not symmetric, if a relation is not symmetric, then there's an example where A is related to B and B is not related to A. So notice on our graph, the point 5, 3 is on the graph because that equation is true. 3 equals 5 minus 2. Since that equation is true, this point is on our graph. But the point 3, 5 is not on the graph. So that tells us that the relation is not symmetric. So you can see that for a relation to be symmetric, the graph must be symmetric across the main diagonal. So the mirror image of the graph must be on the part of the graph as well. Is R transitive? If not, give a counterexample. Well, R is not transitive. Notice that 7, 5 is on the graph. That's because, and also notice that 5, 3 is on the graph. We already discussed that. But notice that 7, 3 is not on the graph. So we have three numbers. 7 is related to 5, 5 is related to 3, but 7 is not related to 3. So our relation is not transitive. Another example, define a relation R on the set of real numbers by saying this: x is related to y means x is less than y. So how do we illustrate that using a graph? Let's start by drawing the line x equals y. So those are all the points on the graph where x equals y. Now what would it look like for x to be less than y? It would be that part of the xy plane. So is R reflexive? Well, no, because 1 is not related to itself. That is, the inequality 1 is less than 1 is false. So we can see that we could have picked any point on that main diagonal. They're all missing. Any one of those missing tells us that this relation is not a reflexive relation. So there is not a point at 1, 1. Is R symmetric? Well, you can see clearly not, because notice that the point 0, 2 is in that relation because 0 is less than 2, but the point 2, 0 is not. All right, is R transitive? Well, yes, it is transitive. It's a property of real numbers. So the relation is transitive. Let's go on. Example 6. Define a relation R by saying that xry means this: x squared plus y squared equals 1. So illustrate R using a graph. Well, the graph is going to be the graph of a circle. Circle of radius 1. Is R reflexive? Well, no. There are some points on the main diagonal that are not on the circle. We can see that there is no point at 0, 0. Is R symmetric? Yes. We can see it's because the graph is symmetric across the main diagonal. So if I pick a point there that's on the graph, its mirror image across the diagonal is also on the graph. Is R transitive? Well, no. One, 0 is on the graph, and 0, 1 is on the graph, but 1, 1 is not on the graph. 1, 1 is missing. So 1 is related to 0, and 0 is related to 1, but 1 is not related to 1. 1 squared plus 1 squared is not equal to 1. Example 7. Define a relation R on the set of real numbers by saying that xry means that xy equals 0. Illustrate that using a graph. Now, how do I illustrate that with a graph? Well, remember the zero product property says that x times y equals 0 only happens when x equals 0 or y equals 0 or both. So there's the graph of R. It's the axes. Is this graph reflexive, or is this relation reflexive? Well, no. You can see that the point 1, 1 is not on the graph. So 1 is not related to 1. It's because 1 times 1 is not equal to 0. Is the relation symmetric? Well, for that we think about the symmetry of the graph. Look at all the points that are on the graph. All the points that are on these axes. Their mirror image across that green line, their mirror images are also on the graph. In terms of the equation, we could say this. If xy equals 0, then yx is equal to 0. So if x is related to y, then y is related to x. We could have done something like that earlier with this example of the circle relation. So if x squared plus y squared equals 1, then y squared plus x squared equals 1. So if x is related to y, then y is related to x. Let's go on. Is R transitive? Well, this is a little bit tricky. The key is this. One is related to 0, and 0 is related to 1, but 1 is not related to 1. That's because 1 times 0 is equal to 0, and 0 times 1 is equal to 0. But 1 times 1 is not equal to 0. So not transitive. Example 8. Define a relation R on the set of real numbers by saying that xry means that xy is not 0. What does that mean? That means that neither x nor y is 0. So how do we graph that? Well, we have to start by drawing the axes dotted. And then we shade the region for our relation. So everywhere in the xy plane that's not on the axis is part of the graph. So is R reflexive? Well, this is interesting. Notice that most of the points on the main diagonal are in the graph, but there's one point that's not. 0, 0 is not in our set. 0 is not related to itself. That is, if I write this, that's a false sentence. If I say 0 times 0 is not equal to 0, that's false. Okay, is R symmetric? Well, yes. We can think of it graphically, that any point that's on the graph, any point that's in one of those regions that's shaded, has a mirror image that's also on the graph. But we could also just think of it in terms of the definition of the relation. If xy is not 0, then yx is not 0. So if x is related to y, then y is related to x. Is R transitive? Well, it turns out yes, because so if xy is not 0, that is if x is related to y, and yz is not 0, that is if y is related to z, then all three of those letters, x, y, z, are non-zero. Then x, z will not be 0 because neither x nor z are 0. So we see that if x is related to y and y is related to z, then x is related to z. Now prove or disprove. If a relation R on a set A is reflexive, then R inverse is reflexive. Well, this is actually true. We'll prove this using a proof by direct proof. So we have no choice about how this has to start. We start by introducing a generic particular element that satisfies the hypotheses. And then we also have no choice about how this proof has to end. It has to end with that statement. Now let's work backwards. This is a defined term. R inverse is reflexive. What does that mean? Well, we have no choice but to precede that with what it really means. In order to get to where we can say that R inverse is reflexive, we have to first have said this. For all little a in set capital A, little a R inverse A is true. Now think about this. How do we get to that? That's a universal statement. So the only way that we can possibly get to that green statement is to have at some point introduced a generic element A. And we have to, what do we have to do with that? We have to show that So these two statements, suppose little a is in capital A, therefore this is true, that's what we have to do in order to be able to say that, that this green statement is true. So we know that somewhere at the very beginning we have to introduce this generic element of set capital A. Well, that's going to be our statement 2. And again, we have no choice because we need this pair of statements in order to be able to say this green statement. Well, now look, we know that R is reflexive. So because of that, we can say the following. Well, now look, we know that ARA is true, and so therefore we can just right away say that this is true by definition of R inverse. So this black statement is statement 4, and the green statement is statement 5, and its justification is by 2 and 4. And the red statement is statement 6, and it's justified by statement 5. That's the end of the proof. One more example. Prove or disprove. If a relation R on a set A is transitive, then R inverse is transitive. Well, this is actually true as well. Let's prove this. Let's do a direct proof. So we suppose that a relation is transitive. So that's a generic particular element. And we have to end by saying that R inverse is transitive. Now, we have no choice about what has to precede this last statement. Before we can say that, we have to previously have said this. So that's what it means to say that R inverse is transitive. So the justification for the final step would be, well, let's work backwards from there. This expression has defined terms in it. So what does that mean? A R inverse B means BRA. So before we can say this green statement, we have to have previously said this black statement. Once we say that black statement, the green statement follows just by definition of R inverse. But watch this. This is an AND statement. The AND operation is commutative. We can put this in a different order. So if we can get to here, then we can get to here. Because the only difference between these two lines is the order in which we're saying things in that AND statement. And AND is commutative. But look, this black statement is true because we know that the relation R is transitive. So we actually can justify the black statement. It's statement 2, and it's true by statement 1. And so that means that the next black statement is statement 3. The green statement is statement 4. The red statement is statement 5. And that's our proof. That's the end of that example, and that's the end of the video. Thank you.